Good morning, everyone. Thank you so much for joining today. I am Bhumika Makwana, founding engineer and head of computer vision and analytics at GalaxEye Space. How many of you have actually worked on building GenAI application from scratch? Okay. And how many of you have tried to use different modalities of data to build one? Okay. So this talk is centered around multimodal fusion or multimodal AI, where how you can use or build an application using different modalities of data, not just vision and text that we usually encounter. The motivation of this talk is typically from how the AI has evolved from traditional to the modern AI, where people have moved now towards adding different modalities of data, like with example being ChatGPT and Gemini. And the users being mostly from not just the ML experts, but more general purpose user, not having any background from, not having any technology background very specific to deep learning or AI. The origin, the inspiration or the motivation of all this comes from how we as a human combine different senses to interpret different information from different receptors, and how we interact with the systems and the world around these days. Typically, comparing this to the machine world, the receptors could be related to the sensors, different sensors responsible for collecting different information, and cognition, where we use our brain to collect and combine different information and derive some insights, to more AI and other information system when it comes to machine world. Moving on to how multimodal fusion has changed the game, how it has evolved. So typically this is an example of language and vision models. Language evolving from BERT to GPT-3 to GPT-4. Whereas when you see the transition for vision and vision plus language models, the inventions or the groundbreaking inventions have been from CLIP to Flamingo to still there's a question mark, where a lot of research work has or is going on how we can combine language and vision as a two prominent multimodal or modalities to solve multiple problems and use cases in different domains. And what's in for the market? So right now it is said to be 1.9 billion in 2024, whereas it is projected to increase by a CAGR of 30% to about 26.5 billion in 2033. So it holds a huge scope when it comes to different domains and when it comes to different applications. Now, what are the use cases which you can build for using different multimodal data, and where multimodality is actually playing a major role? So the major one being biomedical, precision medicine, or autonomous navigations like self-driving cars, medical diagnosis and surgery, geospatial intelligence, where we or the company where I works on. And coming to the top 3 applications which I could get from the net is Llama Med, which is released by Microsoft on basically biomedical domain, on how the information or how a chatbot kind of application could be created for medical or biomedical comprehension. So it shows an example of how the performance of Llama Med is much better and much accurate in terms of the language it uses as compared to the ChatGPT-4. And they claim 15 hours of training time for this model. Coming to the second example of vision language geo foundation model, which is typically for geospatial intelligence, extracting information for it, wherein if you give any satellite imagery or any drone image or any aerial imagery, you could derive inference like, let's say, how many cars are present in your scene, or let's say, what do you see in the screen, right? Or let's say, what is the location of an object? So it could also say what's the lat long in terms of geo coordinates, and also map it onto a Google map showing that this is the region where this target is. And when it comes to autonomous driving, typically there are two different type of fusion that they say is vision to text fusion and vision to text matching. In vision to text fusion, it's mostly on enhancing the feature representation of the particular object or particular target in the scene, and which could help in typically scene understanding, understanding what's there in front of your car or in front of your vehicle. Also, in terms of object detection and tracking, understanding what's the velocity of the target or what's the obstacle in front of your car by fusing radar and vision sensors. So Tesla has vision sensors, 5 to 6 cameras that they fuse, and radar to understand where the object is and at what distance, right? And when it comes to matching, it's mostly for control and navigation system to understand what should be the speed, what should be the heading angle and the velocity of the target to basically take a turn or any sort of navigation application. Now coming to the main point is what matters when you want to build a vision language model. I'm taking an example of vision language because those are the two prominent multimodalities of data that we usually deal with. The three things that essentially we should take care of is representation, alignment, and reasoning. So representation means how do you represent different modalities of data, right? Let's say I have a text or I have a image. Do I represent it in a vector format? Do I represent it in a matrix format, right? Alignment is how do these interact together how do we combine and how do these interact together to comprehend something, and the third being reasoning or transference is how do you process this data. So once you have aligned them, once you have represented, once you have aligned, how do you combine and process it so that you could derive any inference out of it. Now coming to what we built here is basically combining vision, language, and geolocation information. So vision language being the normal ones. Geolocation means the lat long. For any Earth observation application that you build, it's important that you have an associate geotagging, which we call is to be a geolocation information for a particular thing. This chatbot is responsible for grounding image captioning, whereas given an image, it can describe what are the targets, where are the targets, what's the location of the targets, right? It can also do multi-turn conversation where you can ask multiple series of questions and interact with it based on a given image as an input. And region-based captioning, where you can also select a specific region inside an image where you want to query and get information about. This is typically used in defense applications where you want to understand, or you have pinpointed a particular area and you want to understand what's happening in that area. And you can also give an image and understand what's the location of that image. So I can just upload an image and I can also get what is the lat long of that particular image. How do you go about collecting the data? So the data was collected based on these design principles mentioned. And it was centered around these three tasks, which was detection, captioning, and vision grounding. And what we did was we used ChatGPT for instruction tuning. And annotations and all were ChatGPT 4 assisted. So coming to what is the distribution of data, so based on the different tasks that we mentioned, these are the sizes or number of data that we have, detailed descriptions, multi-round conversations, grounding descriptions, all of that. All in all, there were 306 training samples and a separate 12K instruction set for testing. Architecture was inspired from InstructBlip, and we built our own location encoder to encode the lat long information. You have an image, you have to encode using Makwana or any other vision encoders. You have a Q-former, which basically tries to learn the best representation of an image for the particular instruction that you're trying to give for. And then you pass this through a similarity matrix. So the whole architecture that you see at the right or in the middle, sorry, is taken from clip, and we have a location encoder that we designed. So basically, a bigger challenge for this sort of thing is you have lat long, which is one dimensional, and you have image, which is some d or k dimensional, right? How do you map it? Because you map it to a same dimension for similarity-based calculation, or let's say cosine similarity. So we try to employ different methods rather than just using multi-layer perceptron, which could be one way to solve this. Using a location encoder, which is basically nothing but a series of Fourier. So we did a Earth space-based projections, and then you use a Fourier series in a hierarchical format to basically extract different frequency component from the location information, and then you try to do any similarity based metrics or calculation, and you get the geolocation response. So this is very similar to how the clip works for vision and text. And typically after this, once you get the best set of encodings for the image, you pass it through fully connected and then LLMs to generate the text response for it. So what were the training stages? We trained in 3 stages. First stage was keeping the image encoder frozen and training the Q-former to learn the best representation of an image for the instruction. Second stage was where we tried to learn or train location encoder from the embeddings that we learned already in the first stage. And third stage was keeping location encoder and Q-former both frozen and training the fully connected and LLM. So this was a 3-stage training that we employed to train the model. Maybe we can see the demo in person. But yeah, it's basically once you give an image, you can describe, you can query based on the text. You can describe an image, you can ask also for what's the location of a particular image. And you can also select a particular region in an image and you can understand what's there in it. Coming to the results, we try to benchmark based on these 3 things: detail, position, and the hallucination score. Details on how much detailed response you're getting for a particular image, positions on basically, since we're also querying where the target is in a particular image, so how much better the model is basically trying to say the location of a target, and hallucination score. Yeah. So coming to climate change and sustainability, where we all are heading towards, a bigger challenge it comes is you usually don't have text and vision as the 2 modalities of data to work with. And here I've tried to list different platforms, different modalities, and different applications when you have to work with when you are trying to solve any climate-based or any sustainability-based solutions, right? So what are the platforms from which you get different sort of data is spaceborne, which is satellites, airborne UAVs, which are drones or airplanes, ground stations, any sensor put on ground stations, and shipborne is, let's say, you mount on ship and all, right? Modalities, so in vision also you don't have something that we usually encounter RGB, but you have different bands which we call it to be multispectral or hyperspectral data based on how much bands you have. Multispectral, apart from RGB, you have an infrared spectrum, thermal spectrum, all of that. Synthetic aperture radar, which is also one type of imaging data that you usually have. LiDAR, thermal, and infrared data. Auxiliary data is data coming from different sources that you have to fuse with in order to get some information or comprehend something. It could be climate data, it could be data from IoT sensors, it could be some spatial database which contains the location information. It could be some elevation model, generally we use DEM or digital surface model or digital elevation model, which compasses of the elevation or height information of an object on the surface of Earth. An application being disaster management, agriculture, air quality monitoring, or it could be defense or any other applications, right? So you have to work with different modalities of data which usually not many foundation models are built to account for it. A simple example of how and why you need all of this is in case of hurricane forecasting, where basically you want to understand the velocity, you want to understand intensity, and you want to understand the after effects of the hurricane that would be caused. And for this, we simply try to use three different sources of data. One was vision, which were the satellite imagery or drone imagery of a particular area before the incident happened and after the incident happened to train the model. Weather data, which is whatever data you are getting from weather forecast data, climate data, air pressure, all of that. Historical data of the hurricane, what was the trajectory that was followed, what was the lat long, and how it traveled to a particular region. Yes, so I couldn't reveal much of the detail. This is something that we have built and not yet patented, but what you do is you have a satellite imagery pre-disaster that you input to some model like CLIP, and we have used image encoder for it. And the encoders, you get embeddings E1, E2, E3, E4. Similarly, for weather and historical data, you pass it through the encoders and get their embeddings. And then finally, this embeddings aligned, which was the second thing that we mentioned that you should consider when you're building multimodal models is alignment. So what we did was we tried to use some cross-attention based techniques to combine this different embeddings of vision and weather and historical data together to predict the track forecast. So it predicts the location of the track or how the track would be followed or how the trajectory would be. Where this is useful is to understand what are the regions that would be probably cause or it would be sent around for the damage and what is the significance of damage so that you could account for different Now this was the output that we had, the red one being the predicted one from the model and the black one being the actual track that was followed. So this was some 2015 hurricane model that we tried to, 2015 hurricane trajectory that we're trying to display here. And now coming to why multimodal AI is needed and what is the scope of multimodal AI when it comes to Earth observation and tackling various climate change and sustainability problem. Is there doesn't exist much of the foundation models that actually account for these different modalities. As I mentioned, even in vision, you just not deal with the RGB data, but you deal with multiple spectrum of EM. And how do you build models for it? Right now, a foundation model doesn't account for it, and this also results in lot more huge amount of data and lot more amount of training and the parameters for the models. Second is there's not much understanding of how we can represent different sort of data since we have different representation of different modalities of data. How do you bring it together? How do you basically have some sort of alignment for all this sort of data so that you can actually encompass or build an application on top of it? And and there are different platforms from which the data comes. So it's not just satellites, there are multiple satellites out there having different resolutions, having different bands, working for a different EM spectrum. Also different imaging data, not just RGB, but also radar data, which is synthetic aperture radar data, which is somewhat like a black and white image to comprehend. So these are the challenges when it comes to using multimodal AI when it comes to Earth observation or any other sustainability problem that you want to solve for. And what's the future? The future is a lot of work, a lot of effort being put to basically solve these problems, like deforestation. So many companies are working towards understanding how the forest has been degraded, and you just don't need, So a very simple example to quote here is when it comes to, let's say, wildfire, right? And you want to understand where the wildfire has happened, what is the extent of damage and all of it, right? So You can't just use satellites optical data, which is, let's say for now, RGB data, because you cannot see beneath the wildfire to understand what is the source of wildfire, right? So for that, people use synthetic aperture radar, which has a capability of passing through the smoke cloud and all of these, so that we could understand what's happening. So although vision data could help you understand that there's a wildfire and this is the extent of it, you cannot understand what's the source of it and what's the extent of damage, for which you have to use another vision modality data, which is synthetic aperture radar, right? So different applications like deforestation, understanding crop growth and all in agriculture, air quality, and wildfire, extent of ice melting and how it's impacting the global climate is something that we can look forward to. Yeah. So coming to the end of slide, this is all about how multimodal fusion could be used to basically cater various problems when it comes to Earth observation, when it comes to climate change, and when it comes to sustainability. Yeah.
Thank you for the wonderful talk. Can you explain a little bit on how you used ChatGPT 4 or 4.0 to annotate the specific information that you are trying to annotate? Because you are trying to annotate across multiple modality. Can you throw a light on that?
Yeah, so there's something called as instruction tuning, right? So once, basically, if you see the model architecture that we have built, you basically try to extract the vision embedding pertaining to the instruction. So whatever, what we did was, based on the normal response you have, we try to fine tune it using the ChatGPT response.
Okay, thank you.
Hi. So my question is related to the architecture itself. So one interesting thing I observed was that before the dropout layer, you have implemented the ReLU layer, right? As in, you have used ReLU over there. So it's a two-part question basically. So first I wanted to understand that whether the data that you are using is very sparse, because considering different modalities are considered and accounted for. And if it's that way, then why have we used ReLU, not the leaky ReLU, or let's say another activation function before it? Considering it can sort of cause more exacerbation and hallucination going forward. So just wanted to sort of understand that.
So majorly ReLU was used for the location encoder that we mentioned, right? So basically you have lat long information that you want to encode into a space, let's say d-dimensional, so that you could perform similarity based calculations, right?
Okay.
Very similar as to CLIP. Now in that case we have used EEP, and then we have used Fourier series, right? For that, for those sort of data where you have frequency information extracted for different scales, ReLU works much better as compared to leaky ReLU.
Even with this sparsity?
Yeah, even with this sparsity.
Got it. Okay. And Fourier transformation, you have applied it before, or like if that's after the
You
transformation?
project it to, so you don't have use a lat long, you project it to a Earth observation projection space, and then you try to extract different frequency component for different scales using Fourier transform.
Understood. Got it. Thank you.